So I'm Cameron Miller. I'm the Deputy Division Chief of the Sensor Science Division, so we cover a lot of different measurement capabilities. Today, I only have enough time to figure out what the problems are. I will be presenting pitfalls for making these optical measurements. I will provide some solution. There's a whole crew of folks that work on these type of measurements with me. The good thing is I am the division chief, so when I ask them to help them, they're a little bit afraid to say no. So I did what I need. In the US, there's a number of documentary standards going on from HSI and ASHRAE, and I would call these more what I call test bed type of measurements, validation that the system works in a controlled environment. And when you look at these, there are no radiometric requirements for the measurement of the device. They're all biological indicators. And that's just because radiometry is somewhat of a bad name. There is nothing wrong with the radiometers, the spectrodiometers. You just have to know the characteristics of the devices to understand what you're measuring. So when you go to make a measurement, you need to have somebody who's versed in radiometry to help you to make sure you're measuring the photons you think you're measuring. I was sent this photo about 5 years ago from Barry Hunt, where he has 3 different types of devices inside one of these chambers, and you can see that you're reading a factor of 2, 200% difference across these devices. And I was told to fix this. We are still working on fixing this and understanding why we see these differences. For this particular case, a lot of it is the devices are calibrated in a collimated beam, where it's going one direction. But now I've put it in that area where it's seeing photons from every direction. And that's not necessarily how the device was created to measure the photons. CIE has put out in 220 where they have a lot of characterization and calibration methods for UV radiometers, and you can provide you a lot of indices to describe the characteristics, but there's not much educational information in there. It's not much how do I really do this. So in the US, the IUVA and the Illuminating Engineering Society put an MOU together, and we're working on several documents to be able to measure the photons. One of those off the list, the top there is measuring low pressure mercury tubes. Believe it or not, there is not a standard for the measurement of these. There is an ISO standard for tubular, single tubes, but how to measure bent tubes, S tubes, there is no standard. We have put together a measurement methodology for measuring UV LEDs. There was LM85, which is for visible LEDs, but we have to take a step back in time because UV LEDs are sort of where visible LEDs were in the 90s, and there's a lot, 1990s, and there's a lot of state traps and problems with making the measurements. So we had to come up with new methodologies, and that's summarized in LM92. For extra sources that we're talking about here, LM93 covers that, and there's a new standard hopefully coming out by the fall, which measures the radiant intensity distribution, basically where are the photons going out of a device that I plug into the branch circuit, independent of whatever technology is producing the photons. This is the apples to apples type of measurement. And then there's this fifth one, calibration and characterization of these detectors. And this is where we want to provide much more educational information to the end users on when they get a radiometer, how to use it properly, to understand the idiosyncrasies of their device, and to have a communication with the manufacturer. In that first example I gave you, there was a lot of what we call cosine correction problem. So when the optical radiation comes in and they radiate something, that's the number of watts falling on a meter squared. When it comes to the device at an angle, it is now extending that projected angle out there that goes by the cosine. So you would expect your detector to have a similar response if you were to take a source that points down and move it over here to 45 degrees. You see the square root of 2 difference. As you can see by these curves here, the blue curve on the outside, which is on top of that one orange curve, is a cosine response. But not all of these follow that. The brown curve in the middle there, not the center brown one, but the one that's alveolar-based, we can see by 60 degrees, the device is hardly seeing any optical radiation. So when I insert that into my chamber, any of the photons that are coming in from greater than 60 degrees, that device doesn't see. We can do modeling and go with corrections to fix that. And this is what we did. We worked with Amy Parrish group in Berkeley around 2020, summer 2020, I believe. They were comparing some of the photochroma dots to their radiometers, and they were seeing large differences. So somehow they found us and called, and we talked to them and figured out what detector they were using. And you can see by the orange curve up there, that was their cosine response as opposed to something like the blue. So their device wasn't seeing hardly any photons off the wall. And to get the same value, the actual value, they had to multiply the radiometer signal by 2.9. So 290% correction on this device. When they did that, they were very happy because we started lining up with these polychromatic dots they were using. So there's a paper out there where they worked on that. Even if you have something that's reasonably close to cosine or appears close, you can still have, this one produces a 45% difference. And it's under measuring how many photons it's seeing. Remember, out of the outer regions, it's not seeing that. So you need to be able to look at your application and understand the characteristics of the device you're using to make those measurements. Another one is reference plane. So you're measuring at some plane. This is when you measure that array, it's at some plane. Now, when you look at these different detectors, you say, well, maybe that's where the black part is on the top. Maybe that's the plane. For many of these, it's below that black top. Now, and many of you would say, well, it's not big a difference. But remember, the radiation coming out of these devices typically follow an inverse square law. So when you double the distance, you go down by the square. So, compliments to Holger, because we could have figured this out and done this plot, but he sent me one, so I just put it in there. For this particular device that he was using, there was a small offset on the reference plane compared to that top surface. And if you're 20 centimeters away from measuring your source, where you can see what I want to get as you get closer to that source, your error goes up significantly because of this reference plane difference. So you have to be well aware when you're measuring something and you're working at close distances that you know where the reference plane of the detector is, and you're aligning that with whatever sample illumination or such that you're doing. These are the two bigger problems that can be adjusted for in delta if you know the properties of your device and know the application of how you're going to use it. Now, many times folks say, Cameron, how do you actually know what you're talking about? What is the standard? What is the gold standard? How do you give me this responsivity? How do you really know that? Where does it come from? And that's what our job is at the National Metrology Institute. And the way we do it is we use 3 different methodologies to get there. So what we typically do is we use what they call electrical substitution. So I have a cavity that's kept at liquid helium temperature, and I put a laser into this cavity that absorbs all the light, and it creates a temperature rise. I turn off the laser. I have a resistor on that cavity. I put in a certain amount of electrical power to create that same temperature rise. I know how many electrical watts I put in. I know how many optical watts I was seeing. And now I can transfer this optical watt method to whatever detector I'm using. So now I have a means of getting optical watts onto some detector. And then I have now a calibration facility that I can transfer that information off of those detectors to other detectors and start propagating through the line. So we have this ultraviolet spectral comparator facility, which we've completely revamped because of the needs in manufacturing, because of the needs in germicidal UV, to get as low an uncertainty as we can for these situations, that we now can calibrate radiometers with respect to wavelength for their responsivity to power. And this is some of the pictures and the images we use. And we can get a variety of different energy levels onto the device using different sources that go through the spectroradiometer. But when I get to, I know this is 254, but 222 devices have a similar problem where you're using some sort of broadband detector underneath the filter that is just to only let the 222 through or only let the 254 through. And this is a logarithmic scale showing that. But as I get out to longer and longer wavelengths, some of it's sneaking through. If I look at it logarithmically, it was linear, this was logarithmic, we can see that these longer wavelengths basically are about the same signal as what I'm trying to measure. Is that important? Do I need to know that? Well, it depends on your situation. If I am in a room with halogen bulbs, and I'm typically at 500 lux is the surface light that I have, you're measuring about 1.73 microwatts per centimeter squared out of that device. There's no 254 in the room, but you're measuring 1.753. For white LEDs, it's nice. We hardly have any of that residual signal. But if you're standing in a room where you have sunlight outside coming through a window, you'd be measuring 3,000 lux is a typical number on a nice day coming into the room, and you have 7.68 microwatts per centimeter squared. So you have to know your device and your application. So a lot of these measurements can't be made when there's light on in the room. Because if you go to figuring out how much is the limit that I'm allowed, and this was at 254, I'm looking to be able to measure less than 2.1 microwatts per centimeter squared, and I've already got these extraneous signals screwing everything up. So this is something that has to be aware of. And there's multiple devices that have multiple spectral responsivities. And this comes up, knowing what device you need for what your application is. This is some of the variety of sensors that a colleague of mine, Tom Larson, has measured with you. When we look at 222, some devices are better than other ones. So now, when we look here, we're getting into some of the spectroradiometers. So I put sort of what the NIST scale is. This particular spectroradiometer measures pretty close to what I had over here. Doesn't have much of that stray light problem because of actually screening it out to lower power wavelengths. But as I get into different detectors that are intended to measure 222 nanometer light, they're not all the same. So if you're going into a system to validate it, make sure the lights are off and it's at night if you want to actually get good measurements. So now we start bringing up spectroradiometers. So at NIST, there's two ways that we go through this scale realization. One of them is using a synchrotron. So it's basically a captured electron that we ramp up at a magnet until it goes to about the speed of light. And when electrons go at the speed of light, they put off light. And it goes as a Schwinger equation. So this particular device, we can get the peak distribution is at 6 nanometer light. It's a little too blue for us. But we can ramp down that electron and peak it so that it almost looks exactly like the deuterium spectrum, which is what you're seeing here. Now we can calibrate our system using this known absolute device, because it follows quantum mechanics. If we know the ring, we know the magnet, and we know the speed of the electron, the energy of the electron, to get this deuterium lamp and calibrate deuterium. So this is how we do it in this. I think we're still the only one that do it this way. Other people heat up a black body. What's that mean? So what they do is they take some sort of black body, which is shown in the upper left-hand picture there. There's all this electricity going into this cavity here. And they take it up to about 3,500 degrees. And it puts out a black body radiator curve, which is shown in the lower hand corner down here. I can measure that absolutely, and it'll follow the black body curve, and then I can calibrate that signal against lamps and disseminate it in such a way like that. Problem with that is, this doesn't look like the deuterium lamp, which is eventually what I want to calibrate with these devices. And I got a lot of red and infrared light here. But if I use a good spectrometer, the final good news, and calibrate that with these two devices, this is the responsivity curve at different wavelengths from 200 and 400 for a good device. And what you can see is that we have the spectrometer's irradiance measured divided by the NIST scale. The red curve is using the deuterium lamp to calibrate it. And the blue is using this FEL, or this lamp, halogen lamp, to calibrate it. And you get the little bumps there at 370. That's a tough region to measure for a number of reasons. But they basically agree within 1%. So if you know what you're doing, you can do this within 1%. Now this particular device has good stray light rejection. And it goes even as far to correct for the out band stray light. What is out band stray light? So this is a variety of different spectroradiometers. And what I've plotted here is it's indivisible, it's basically a helium line. And you can see that there's different bandwidths, some are fatter, some have more resolution. Some have a lot of signal where there is no light, where they shouldn't. And if you're measuring something of that nature, using one of these devices that does not reject this out-of-band light, you're going to get incorrect results. You're going to tip over your exposure limits very quickly. My colleague in Zhang, about 2008, figured out that if he scanned along this spectroradiometer, and you can see that peak moving along, he could measure this out-of-band light and then correct for it. So he creates this matrix, inverts the matrix, and when you multiply the spectrum you measure, you will correct for all this out-of-band light. So it takes for something that is rejecting maybe 10 to the minus 4, 10 to the minus 5, takes it into that 10 to the minus 6, 10 to the minus 7 rejection well. So now you can do a very quick measurement with a device by getting this, as I call it, a out-of-band stray light correction matrix. And there's a variety of different spectroradiometers that have this included on them. When you apply that to the light you're measuring, this is an example of green LED, but it works just the same as our 222 nanometer peak light that we're working with. This out-of-band light, so you see this is, the dark line is the curve that it just measures. But when you correct for all of that out-of-band stray light that's caused, you see you sort of get that scatter. So your sub-1 count measurements, actually, you're below a single unit that this device can measure. And it eliminates that. So making a much better measurement. You don't have to worry about falsely including wavelengths that are not part of the actual measurement. Then there's still one more example I'll show you that is driving me nuts. This is all you 222 guys. So this spectroradiometer I use, calibrated with my deuterium lamp, measure 222 nanometer lamp, get a signal, get a spectrum. This is a responsivity curve. So this is, and then I come back a couple days later and I repeat my measurement and I get a different number. Come back a couple more days, get a different number. The responsivity of this particular spectroradiometer changes on the order of 10 to 15% of 222 when it is exposed to 222 nanometer light. To let it relax takes like a month and a half. So this like put me out of business. And I put one of these 222 nanometer lamps under my spectroradiometer for a while. The weird thing is, many people would say, this one has a particular fiber feed to it. And fibers can solarize, so their spectral transmittance will change as you put high energy photons in there, these F centers, color centers, and traps electrons and such. And the electrons will wander away over time. And we thought, well, that's what that is. Then you look at the responsivity. So day one here is the red curve. And as I expose it, it goes up. So for each photon, I'm getting more electrons. This doesn't make sense. So somehow the CCD or the electronics in the system are getting fouled up in there, or it's photo bleaching, degrading. I have no idea what it is. We haven't been able to track down this. But there are different products out there that don't exhibit this. So in the standards business, you would go into something that's much more stable. So as far as what we do offer, this is what we do our radiometry on. This is called photometric bench. It's got a source slide where you can see sort of the red sphere and the red light. That's where the sources sit, and that slides back and forth. You have a detector stage for the gold boxes and the various things. And then they can move the distance within respect to each other. We have movements on the order of 50 microns to keep the distance as best we can, because that's usually one of the largest problems in line, like I talked about that reference point issue. But now we can calibrate radiometers in a collinear fashion, but we can now provide all that information. We can then calibrate it against a xenon lamp that has a glass window, to know what that extraneous out band is. We can do stray light correction to radiometers. And all of this information eventually will end up in that document, so you have an educational guide, because I'm not sure how it is in Europe, but there is, maybe somebody can correct me, I don't know if Colorado has a radiometry course for their students. It is not something you find typically in the US. I mean, I'm a physical chemist, went to NIST and somehow became a radiometrist or photometrist, or whatever you want to say, doing all this work. So, number of pitfalls, but hopefully we're trying to put these out there so people know what they're dealing with, and then we can talk about it and make the measurements better. That's it. Any questions?